right, Lewis structures. So much fun. These are literally one of my favorite things to do. I think drawing Lewis structures is a blast because I'm a loser. No, I'm kidding. It's still a lot more fun than some things in chemistry. When you learned this last year, you learned Lewis structures of atoms, and then you learned kind of like how to transfer electrons and ionic bonding. Remember drawing Lewis atoms, electron dot structure, not electron dot, just Lewis structures of atoms, and then drawing an electron, drawing an atom, transferring electrons from one to another. That whole ionic business, it's truly not a true format. We do not draw Lewis structures of ionic bonds. So you can erase that from your head. You'll never be asked to do that because there's no true format for that. Let's really quick, though, before we begin, just remember how to do Lewis dot structures of atoms. So if you have an atom like nitrogen, does anybody remember how to do the Lewis dot structure? What do you take? Number of valence electrons. So looking at the periodic table, how many valence electrons does nitrogen have? 5. We all remember how to find the valence electrons. It's equal to the group number, the Roman numeral, right? And we know if we looked at the electron configuration, we could figure it out too, okay? But anyway, it has 5, so we're going to place 5 electrons around. We're going to pair the first pair to kind of represent the s orbital, 1, 2, and then the rest we're going to do like Hund's rule, 3, 4, and 5. Now, I don't care where you put the pair. There's no set rule. You have to put it on top or on the left or whatever. Put them wherever you want. You just have to have at least one of these paired. So if we have carbon, how many valence electrons? 4. So we'd go 1, 2, 3, 4. All right? We pair the first because they're S's, and then we spread the rest out using Hund's rule. Okay? That's all there is to that. That's all I'm going to talk about because, again, that's just a little reminder. It's not something specifically you're going to get tested on. But if you see one, I don't want you to freak out about it because it could pop up on the AP because it's assumed knowledge. So when we are doing Lewis dot structures of covalent compounds, we're going to see single bonds, double bonds, and triple bonds. You guys have to learn to be really, really neat. I'm going to be more, my expectations as far as how you're placing your lone pairs and things are going to be a lot higher. So when you draw like F2, and we'll talk about where we get the numbers in a minute, your bond needs to be clearly a bond, and that looks like a triple bond, and it's not. Your bond needs to be clear, and then your lone pairs need to be deliberate and clear. And they need to be in pairs. You can't be like doing this business and expect to get any credit for that. Pairs have to be in pairs. I think some of you are struggling to see. I'm going to make my ink line thicker. Let's make it like that. Okay. So best way to do this is to just jump into it. The first few we're going to do non-exceptions. So everything either needs 8 or 2. Everything needs 8 except for hydrogen. Hydrogen needs 2 to be full. So the way we learn this, and I want you to continue with the needed available shared thing. If any of you go to tutors, they're going to be just saying, count the number of electrons and just put them down, whatever. I don't like that because with needed available shared, you're told how many bonds have to be in the picture, and that is key. Once you know bonds, the rest is easy. So just to refresh, we know how to draw this structure. It's not a hard one. Needed available shared. Hydrogen needs how many electrons? 2. But there's 2 of them, so in a perfect world, we'd need a total of 4, right? How many do we actually have? A is the valence electrons. How many we actually have? How many are available? 1 in each, so there's 2. So we're going to have to share 2 electrons, which translates to how many bonds? 1 bond. So this picture has to have 1 bond. That is non-negotiable. Whatever you get for shared is the number of bonds you have to place, no matter how uncomfortable it makes you. Okay? So we're going to put our 1 bond in the picture. When you're done, I want you to always go back to the A and make sure your picture has that many electrons in it. Of the 2 we put in bonds, we used them up. So we got none left, so that picture is finished. Okay? All right. F2, which we just did, is easy. Again, I'm doing these simple baby examples just to get you to remind you how to use NAS. Needed, how many do we need in a perfect world? Each needs 8. 8 plus 8 is 16. How many do we actually have? Fluorine has 7 for each, right? So that is 14. When you subtract, that means we're going to share 2 electrons. The 2 electrons we're going to share are going to be in a bond. They have to be, so that's our one bond. So of our available 14, we used up 12. We have 12 to pass around. So I'm going to place them in pairs until everybody's full. 2, 4, 6, 8, 10, 12. Okay? Easy one. Forget HF, that's too easy. Let's do NH3. When you have more than one thing attached, like you've got, here we've got one atom and then 3 others that are obviously going to be surrounding, you always have to have a central atom. If you just have 2 things like this, you're not going to have a central atom, so just put them next to each other. But you always have to choose a central atom. Usually the less electronegative atom goes in the center. Okay? With this, it's a no-brainer because hydrogen can only bond once, so it can't be a center atom. So we're going to put nitrogen in the middle, and then hydrogen's on the outside. Sometimes I like to set things up before I actually start drawing. I mean, doing needed, available, shared, but that's your call. So needed, available, shared. How many do we need? 8 plus, each hydrogen needs 2, right? 2 times 3 is 6. So 8 plus 6 is 14. How many do we actually have? Nitrogen is 5, and each hydrogen is 1. So 5 plus 3 is 8, meaning we're going to share 6. How many bonds is that? 3 bonds. So we're going to place our bonds in the picture. Of the 8 available, we've used up 6 in bonds, so how many do we have left? A lone pair, and where do we put it? On the nitrogen. Okay? Now, the more experience you get, we're going to learn the shapes again, so you're seeing things again. When you're drawing your Lewis structure, you're not going to be wrong if you draw the shape incorrectly, but start thinking about, okay, this is trigonal pyramidal, which you'll relearn soon. Just kind of start drawing things the way they're supposed to look. It's going to make you look smarter. It's going to open up some possibilities in free response questions, knowing the shape, and if you see it visually, you might figure something out that you might not have had you drawn it in a weird two-dimensional way. So try to draw it as it actually looks. All right, CO2, needed, available, shared. How many do we need? 8 times 3 is 24. Carbon needs 4, and each oxygen needs 6, so 12 plus 4 is 16, meaning we're going to share 8. How many bonds is that? 4. All right, so when we align this, what goes in the middle? Carbon. Carbon loves to be in the middle, okay? Carbon undergoes catenation. If there's another carbon around, it's going to start making carbon chains. It likes 4 bonds. It likes to be in the middle. So we're going to put an O and an O. We have 4 bonds to place. What are we going to do? Okay, I'll take that and I'll accept that as one possibility, but now you're in AP chemistry. Is that the only possibility there is? No. What else could carbon dioxide do? Triple and a single, or single and a triple. These are called resonance structures, and tomorrow we're going to be going over this. You only need to draw resonance structures when I ask you for them specifically. When I don't ask you for them, I want you to draw the best or the most prominent resonance structure, the one that contributes most to this hybrid. You learned to just do this top one, right? Like that was your first instinct. And this is the best one, but you haven't learned why. And that's what we're going to do tomorrow. You're actually going to know why this one is your better structure than these other 2. So let's go ahead and fill all of these in. Of the 16 available, we used up 8 in bonds. That gives us 8 that we have to pass around, so 4 pairs. So for this one, I'm going to put 2 pair and 2 pair. And then on the bonded oxygen, it has 3. How many pairs do I put? Just 1 there. And here I put the other 3 pair. Do you see why? Because they only need 8 to be full. And then this oxygen, I'm going to put 3 pair. And this one, I'm going to put 1 pair. Okay? Starting tomorrow, we're going to talk about why this is the best, and if you were asked, though, to draw all resonance structures, I would expect to see all of them. Save some space, because I'm going to add a couple to the bottom of your page. I'm going to add a couple new ones. Actually, you can cancel this guy out. We're going to make him something different. CCl4, really easy. C in the middle, C on the CL's on the outside. Needed, available, shared, and then how many do we need? 40. 8 times 5 things, 40. Each carbon needs 4. Chlorine 7. 7 times 4 is 28 plus 4 is 32. So we're going to share 8. How many bonds is that? 4 bonds. So we have our little tetrahedral thing here. So how many do we have left to pass around? 24, right? So that's 3 pair on each. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Everyone good so far? All right. We're going to add a couple that actually have charges. We need to look at that. So when you see something is charged, you don't change your needed. Just add. You don't have this. You're going to have to add this to your same page. This is not on your current handouts. You do not change the needed. Please don't change it, because regardless of the charge, things need what they need. Nitrogen needs 8. 2 for each hydrogen is 2 times 4 is 8, so that's needing 16. What changes when you have charge is your available. If you have a positive charge, you have that many less electrons, and if you have a negative charge, you have that many more electrons added or subtracted to your available. So nitrogen has 5. Each hydrogen has 4. That's 9. Right there, you should kind of feel funny. What's wrong with that being 9? It's not an even number, so when you subtract, you're going to be sharing an odd number of electrons. That's kind of an indicator something's up. Well, this is positively charged, so it means we have 1 more or 1 less electron. 1 less. So we don't have 9. Instead, we have 8. That electron has literally been taken away from the valence, so we have 1 less. So we're going to share 8. So all of our electrons, all 8 of them, are going to be in bonds. Nitrogen being in the middle. We're going to have 4 hydrogens on it. This is ammonium. Remember this polyatomic? And if it's charged for today and today only, you do that. Once I teach you formal charge tomorrow, you can do it a little bit differently. This is always acceptable, though, when in doubt. Anything that's charged. This is telling the person looking at this picture that this has 1 less electron than it should based on the availability of electrons. All right, NO3. Needed, available, shared. How many do we need? 8 times 4 is 32. We actually have 6 times 3 is 18 plus 5 is 23. What's wrong with that? It's odd. We need to add 1, right? Because it's an additional electron making 24. So how many are we going to share? 8. 4 bonds have to go in this picture. So we're going to have, how are we going to place those 4 bonds? Again, don't argue with the shared. You have to have 4 bonds. What do you want to do? Make one a double, and then the other one's single. What does this lead you to believing, to seeing now? What is this? What can we draw? We can draw resonance from this. Let's finish this one out, and then I just want to talk for a couple seconds to talk about the difference between the resonance you're seeing here and what you saw with carbon dioxide. So double-headed arrow, we can draw the placement of the double-bonded O here. Now let's double check, make sure, do we have the right number of electrons in the picture? Do we have 24? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So always verify. If you're on a test, there's absolutely no reason you can't sit there and make sure you have the right number of electrons. Don't be too proud to do a little extra work to verify you did it right, especially if you have extra time. So on the AP, you should never be sitting idly by. If I hear, I'm going to ask those monitors, if I hear that y'all are sitting there, I'm done closing your book being all haughty. No, you need to go start checking things like this, okay? So we need to put one on this O. Now, the reason I drew all these is I want to show you something. Do you see how all of them are pretty much the same structure, right? We call these equivalent resonance structures. They're the exact same in energy. The only difference is where the double bond O is. But it's always a double bond between N and O. Double bond between N and O, double bond between N and O, double bond between, nothing else is different. So we call these equivalent resonance structures, and they each contribute equally, 33.3%, to the hybrid of what nitrate is, to that hybrid, okay? On the previous page, carbon dioxide, are these equivalent resonance structures? No, we're going from a double bonded CO to a triple bond and a single bond CO. These are not equivalent. Now, these two are equivalent resonance. So within themselves, they're 50-50, but this guy and these two are different percentages contributing to the resonance based on which is going to be better, which we'll talk about tomorrow. But I just wanted you to see that these are equivalent, this one's not, and then this next page, people are like, why do we have to draw them? They're all the same. Well, theoretically, yeah, but all those electrons actually resonate between the pi bond breaks and reforms between the different oxygens, so they're really not the same. Okay. So now let's do the exceptions. With our exceptions, there's two additional you need to know. The first is boron the moron. The only thing you need to know about boron is he can only hold a max of 6 electrons. Boron the moron's down here. We call him the moron because he's deficient in electrons. There he is right there. Okay? Now, beryllium. There are some examples coming up in your homework, which I'll tell you, but I'll just tell you this. Beryllium is usually involved in ionic bonding. It's very, very rarely involved in covalent unless it's like attached to hydrogen. So needing to know that this is only 4 is kind of a waste of brain space in my opinion, but beryllium needs 4, boron needs 6. Now the other kinds of exceptions you're going to see are going to come because of an expanded octet. Anything on the 3rd level and beyond can expand its octet because of what orbitals? D. We have the existence of D orbitals, so we can go from that 8 to potentially 12. The max we can hold are 12 electrons on any atom. All right? So if you have an exception, needed available shared is going to give you the weirdest number, and you're going to be like, how can I do this? That's your indicator that it's an exception. Or you might be able to recognize it before you even start the problem. And if you do, all the better. But let's go through and do these. BF3, needed available shared. How many do we need? Boron needs 6. 6 plus 8 times 3 is 30. 24 plus 6 is 30. We actually have 3 plus 21, 24. So we're going to share 6. So boron the moron goes in the middle. Least electronegative goes in the middle. And halogens, unless they can expand their octet, they're not going to be in the middle. Now, some of them will, the big ones, but not these guys. So they're always on the outside. So 6 electrons means we have to have 3 bonds. How many electrons do we have left? 18, right? So we're going to start passing those around. 2, 4, 6, 8, 10, 12, 14, 16. And that's good because boron is full with those 3 bonds. We're going to change this SF6. Oh, we got PCl5. I want to change SF6 to XCF4. It's a better problem. All right, PCl5. I'm going to do needed available shared, but I'm hoping you're getting to the point where you can see, oh, that's going to be an exception. Why is that an exception? Why is that not going to follow needed, available, shared? No, that's not the question. But how would you recognize that as being an exception, Isabel? You need 5 bonds, right? Do you see how there's 5 things attached to the central fluorine? Doesn't that immediately dictate that you're going to have an expanded octet, right? Okay, so let's go ahead and do that. We're going to put our phosphorus. Why are we putting phosphorus in the center? Right, and what was our rule? It's the least electronegative. Good. So we're going to surround it with our 5. 1, 2, 3, 4, 5. Now, you could just take the available electrons and place them in a way that I'm going to show you, but let's pretend you're taking the test and you're freaking out and you're in robot mode, and every single one of you get into robot mode. I can tell when I grade your tests. You're just doing what you think you need and you're not like really digging. So let's talk about that. And let's say you're in robot mode. Let's do needed, available, shared and see what's going to indicate, what's going to be your alarm that's going to tell you, whoa, this is an exception, in case you forget. So needed, we have 8 times 6 is 48. We actually have, P has 5. 5 plus 35 is 40. That gives us a sharing of 8 electrons, which is how many bonds? Can we do that? There's your indicator. If you get a nonsensible number of bonds, that's how you know this is going to be an expanded valence. So look at your available and place it with the following rules. First step, attach everything singly to the central atom. And then place the remaining on the periphery in pairs. If after that there's any left over, we're going to put them on the central atom. So let's start counting together. I start with the bonds. 2, 4, 6, 8, 10. Now go to the outsides. 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40. Are we done? Yes. If I would have had 42, I would have then placed them as a pair on the center, if there's any extra. Okay? Questions on this one? You good, Peyton? You look very unhappy today. Are you tired? You're happy? Normally you smile. You haven't smiled much today. Yeah. Okay. Focused. All right, let's try XEF4. It's way better than SF6. Why do you think I think SF6 is just a stupid problem? Right. And with SF6, remember I was saying there's a maximum of 12 electrons? So there's no way we could have a lone pair in addition to those bonds. So it's just a really simple example. PCl5, I didn't know. I could potentially have had an extra lone pair there, so I needed to count. This one, it's going to be single bonds all to the center for a max of 12. All right, XEF4. I know this is an exception. Why do I know before I do anything that this is an exception? There's 4 things attached. Why is it not, Marie? Exactly. Xenon's already got 8. So in order for Xenon to take in those extra electrons, it's going to have to expand its octet. That's how we know it's an exception. But maybe you're in robot mode and you just start doing needed, available, shared. So 8 times 5 is 40. How many available do we have? Xenon has 8. 7 times 4 is 28 plus 4 is 28 plus 8 is 36. So we're going to share. Whoa. Are we supposed to attach 4 of those xenons with, fluorines with 2 bonds? No, we can't do that. So we know that we're going to focus on our available electrons. Xenon in the middle, got my 4. What do I do first, Hannah? Bonds to the central. So let's count. 2, 4, 6, 8. Now what, Kate? The what? On the fluorines. Okay. So we're 8 down. 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. Uh-oh. What do I do, Claire? Put the 2 lone pairs on the central atom, okay? And so, very good. We're going to place that and that. Now, here's something that's really important. This is from a grader's perspective. If I see this on the AP, where you have a bond and an electron pair just sloppily placed, like right on top of each other, you don't get credit for it. The reason being is the central atom, based on the areas of electron density, it's got 6 areas. Those 6 areas need to be distinguishable and separate. You can't be piling bonds and lone pairs on top of each other. So it's not me being like, oh, you're just sloppy. There's literally a reason that you need to place your stuff around the central atom very distinctly and very neatly. Okay? And if you do so, you can kind of helps you with shape. Do y'all remember? Anyone want a sticker? What shape is this? Holy cow, come get a sticker. Holy cow. That's impressive. He said he loved Lewis dots, so I guess he wasn't kidding. Oh, okay, that's kind of an unfair advantage then. No, it's okay. You can keep the sticker. All right. All right, so we're going to do a few more practice, and then I'm going to set you loose on your homework because I think you need to do some individual stuff. And these have been chosen specifically for different reasons because they bring up some different issues. We can cross this one out because we already did number 19. Number 16. Yeah, you could do needed, available, shared. But anytime, and this is prepping you all for organic, anytime you have carbons and hydrogens, they always do the same thing. The carbons bond in a chain, the hydrogens go around, and then depending upon how many bonds carbon has, we add them until we get to 4 bonds. So if we have 2 carbons, single bond them, and then what do we do with the hydrogens? There's 4 of them. How do you want me to place them? 2 on each carbon, right? And I can't stop here, even though I might want to, because carbon is not done. What do we need to do to give carbon its 8 electrons or 4 bonds? Double bond it. If you didn't like what I just did, go do needed, available, shared. It's fine. You do needed, available, shared. It's going to tell you there's 12 electrons in bonds, 6 bonds, which is all the available electrons. So you'll be able to figure it out. But just know you don't have to do needed, available, shared on organic substances. All right, HCN. I bring this up specifically because students want to try to change things around, put N in the middle, put H in the middle. They're giving it to you like this for a reason. Keep these elements in that order, okay? Why can't hydrogen go in the middle? It only has 2 electrons, so it can only make 1 bond, right? Why isn't N in the middle in this case? It's not the least electronegative. So don't be acting like, oh, I know better. This goes in. It happens all the time. So just leave it like this. So needed, available, shared. How many do we need? A plus 8 plus 2. 18. We actually have 1 for hydrogen. 4 plus 5 is 10. Whoa, we're going to share 8. How many bonds is that? 4. What do you want to do? Do I have a resonance structure here? No, I don't. And that's another reason I chose this. This is not a resonance possibility. We can't do anything. We can't do 2 and 2 and 3 and 1 and 1 and 3. Why not? I think y'all got it. I'm hearing a lot of good stuff. Hydrogen only needs 1. So that's it. And then we have a lone pair, right? Of our 8 shared, we still have 2 to place to get to our full available electrons. How many do I place? Where do I place them? Who needs it? Nitrogen. Okay? All right. I think this is our last example of the day, and then I'm going to set you free. This one's great. I know this looks like you're putting things in a line, but you're really not.
What is the central atom? Iodine, and that is okay. Iodine is a big enough halogen it can expand its octet and take more than what we think in terms of electrons. But that's because it's iodine, that's how I knew it's the exception. Okay, so I don't want you to think this is going to necessarily be in a line and you can start bonding things in lines. Like I remember a few years back, I had this being done. Okay, you have a central atom. Identify your central atom. Even if it's a repeat atom, you still have a central. And it's that central atom that's going to determine the shape and everything. So this is an exception, but again, in case you don't recognize that being the case, let's go ahead and do needed available shared. 8 times 3 is 24. How many do you actually have? 21, but it's negatively charged, so we have that extra 2. Sharing 2. Can I really bond these things with one bond? 2 electrons? No. So I'm going to take my 22. Okay. Go do it. We'll help you. Don't be afraid. Okay, you're going to, what is he going to do first? Help him out. Okay, 2, 4. Then he goes to the outside. Go ahead. 6, 8, 10, 12, 14, 16, 18, 20, 22. Perfect. That's good. So look how many lone pair, thank you, good job. Look how many lone pair are on that central. Give him a hand. How many lone pairs? There's 3, right? Okay, JD, what do you think? Yeah, it is. He's just like, he reminds me of Rain Man. Y'all seen that movie? He's Vesper Rain Man. So the only thing we're missing, remember, charged. So we have our brackets. Okay, I want you to use the rest of this time to work on that homework. It's easy. It's just drawing. You don't have room on the homework paper, so I need you guys to please do it on loose leaf, or if you're doing it on your iPad, add some pages to give yourself some room. Don't be squishing this stuff. I want to be able to see where your lone pairs are.